Hello, welcome to Sigma Maths. In this video we're going to make sure you understand the concept of prime numbers, factors and multiples. And we are going to go through how you work out prime factorizations, highest common factor and lowest common multiples. Before we jump into some examples, let's have a look at the definitions involved. When it comes to prime numbers, I find that a lot of students tell me that this is a whole number that can be only divided by 1 and itself. It's not quite the best definition that we could have, because there is a number that fits that definition but is not prime. Think about the number 1. This number can only be divided by 1 and itself, but it is not a prime number. So a better definition is a positive integer with exactly 2 factors, 1 and itself. This way, 1 cannot be confused as a prime number, because 1 only has 1 factor. For all the numbers that do not fall into the category of being 1 or a prime number, we call composite numbers. The reason they're called composite numbers is down to something called the unique factorization theorem. This states that every number larger than 1 is either prime or it can be written as a unique product of prime factors. That means that every non-prime number can be written as a composition of prime numbers, hence the name composite number. When we break a number down into its prime factors and write them as a product, which means we multiply them together, we call it a prime factorization. Now we're going to have a look at some examples on how to do prime factorizations. This question asks us to write some numbers as a product of prime factors. That's the same as finding the prime factorization of each number. In the question they ask us to give our answers in index form, which basically means using powers to show how many of each prime factor we need. I'll show you how to do this as we work through the questions. Now the way that I'm going to approach doing a prime factorization is to use something called a factor tree. This means going through and dividing the number by prime numbers and writing them down as a tree as we go. So we start with 36. Now I will always start with the lowest prime number, and I will continue to divide by that prime number until it doesn't go anymore. Then I'll move up to the next one. This is a nice systematic way of doing things, and it means that all of your prime factors will be in a nice order at the end. So 2 is our first prime number, so we'll always start by trying to divide by 2. The way that I'll write this out is to put a line with the 2 on one side, and a line going to the other side with whatever multiplies by 2 to make 36. In this case, it's 18. Now 2 is our prime number, so I'm going to circle it so that at the end all of my prime factors are circled. 18 can also be divided by 2, so I will have a branch with a 2 coming out here and then a 9. Now I can no longer divide by 2, so I try 3. 9 splits into 3 multiplied by 3. I've come to the end of my prime factorization now, and I could write that 36 is 2 times 2 times 3 times 3. These numbers cannot be broken down anymore, and that's the idea of a prime factorization. It is nicer to write this in index form because it means that I only have to write 2 once, and then I use a power to say how many I have. So I have 2 times 2, that's 2 of them, so I put a squared. I also have 2 3s, so I will write 3 squared. Let's try the next one. 120. So I start off in the same way. I'm going to divide by 2 as much as I can. This time I can divide by 2 3 times until I arrive at an odd number, 15. Now I'm going to divide by 3, because 3 goes into 15, and I get a 5, which brings me to the end of the factorization. I will therefore write 120 as 2 to the power of 3, because I've got 2 times 2 times 2 times 3 times 5. Part C, 300. Again, so I'm doing the same thing every time, and you really do just have to get yourself to work through a few of these, and you'll quickly get pretty fast at it, as long as your times tables are good, obviously. Right, 150, 275, can no longer be divided by 2, so I will try 3. To see if 3 goes into a number quickly, add up the digits. 7 plus 5 is 12. If 12 is divisible by 3, then this number is divisible by 3. Now, if you maybe go into a slight panic when you think, oh, I've got to divide this number by 3, but I can't do it straight away, and you're thinking, but I do know it divides by 5, so I'd much rather just divide by 5. You can divide, you can split your factor tree however you like. You'll always end up with your prime factors at the bottom anyway. But I think my method is slightly nicer, mainly because at the end you will always have this line of prime factors coming down from the left and along the bottom, and they will always be in order, which means when you're counting them up, it will be very hard for you to count them up wrong. So, getting yourself to be better at doing things like dividing by 3 is good for your overall skills anyway. So if you can get yourself to do it, then you will end up being a better mathematician. So 75 divided by 3, 25. 25 then splits into 5 and 5. So 300 is 2 squared times 3 times 5 squared. Okay, now we're going to have a look at 168. There we go, so divide by 2 and then divide by 2 again, and we can go again. 21, does it divide by 3? Yes, it does, to give us 3 and 7. So 168, we've got 2 cubed times 3 times 7. Okay, so this method is going to be very useful, especially later in this video when we look at highest common factor and lowest common multiple. It's actually very powerful to be able to break a number down into its prime factors. It tells you a lot about the number and what it has in common with other numbers. We're going to be actually doing our LCM and HCF method using the prime factorization. It's going to be part of the process. Right, 196 breaks down to 98 and 2, which then breaks down to 49 and 2. 49 breaks down to 7 and 7. So 196 is 2 squared times 7 squared. Okay, last one. 220. Right, if you haven't been doing this already, then pause the video and have a go at this one yourself before I show you what the answer is. Make sure that you can do this independently. And so we are going to halve and halve again. Okay, 3 doesn't go into 55. 5 plus 5 is 10. 3 doesn't divide 10. 5 does though, so let's pop that one down. And this time it's 11. 11's a prime number, so we are done. 220 is 2 squared times 5 times 11. Okay, so there we have it. These are the prime factorizations of numbers, and they are written in index form, which is quite a common request in the exam questions. Okay, so this question has given us some information about the number 455. We've been told that 455 can be written as 5 times 7 times 13. They've then told us what 455 squared is equal to and what 455 cubed. That's a very big number. Okay, so it appears that we need to use this information to write these two large numbers that we got from here as a product of prime factors in index form. Now, they've already done the bulk of the work for us here because they've told us that 455 is equal to 5 times 7 times 13. When it comes to this number, so this is part A, sorry, 207,025, because we already know that this is 455 squared, then we can write that as a product of 455 times 455. If we then replace each of the 455s with the product of prime factors, then our larger number has also been written as a product of prime factors. All we need to do then is collect together prime numbers that are the same. So we've got 5 that is squared, a 7 that is squared, and a 13 that is squared. Okay, so you can write them out individually like this, just so you can be absolutely sure that you've got all the prime factors that you need. In part B, we're going to show a slightly quicker method. So this number, which is 455 cubed, what we can do this time is replace it with the 5 times 7 times 13, and then raise that to the power of 3. So basically not having to write it out 3 times. Then we can apply this power of 3 to each of the prime numbers individually. So that would become 5 cubed times 7 cubed times 13 cubed. And then we're done. So questions like this might look very hard, especially part B. If you looked at that question before you thought about the information in the question, then you're going to think, wow, that's going to take me a very long time to break down. But actually, with this information up here, the question is very, very easy. It's just knowing how easy it is. In this question, we are given the prime factorization of a number they've called y in algebraic form. This means that we know that it's split into 2 times 2 times a to the 4, so 4 lots of a, and b cubed. We don't know what a and b are, but we do know that they are prime numbers and that they are larger than 2. It's important that we know they are larger than 2, otherwise we might find that some of these numbers, some of the a's and some of the b's, are actually absorbed into the 2 at the front of the product. What the question wants us to do is look through each of these expressions and work out which ones are factors of y. To know if a number is a factor of another number when you are given the prime factorization, you need to look and see if you can make that number up using the prime factors that you have in the prime factorization. So, for example, 2 is a factor, as is 4, because 2 times 2 is 4. Something like b would be a factor because it's using 2 of the prime factors that you have in the prime factorization. A to the 5, however, would not be a factor of y because it has too many a's. So let's have a look at each one. 2ab. Now the 2 can come from the 2 squared, a can come from a to the 4, and b can come from b cubed. So 2ab is a factor. 16 a to the 4 b cubed. Well, first of all, a to the 4 and b cubed, that's fine because they come straight from the prime factorization. However, the 16, this is the bit that's a problem because we only have 2 times 2, which is 4. This would require us having 2 times 2 times 2 times 2. We'd need 4 of them in order to make 16. So this number is actually going to be larger than y, therefore it definitely cannot be a factor. A to the 4. Well, that would require 4 a's multiplied together. And we have 4 a's multiplied together in our prime factorization. So yes, this one is a factor. ab to the 4. Well, we'll start with the a's. We have enough a's because we have 4 available and we only need 1. The b's, we need 4 of those. But our prime factorization only has b cubed, so 3 b's. So because of the b's, this is not a factor. 4a squared, b squared. Well, the 4 is fine because we've got 2 times 2 from our prime factorization. A squared, yep, that's all good because we have 4. And b squared is also fine because it's less than the b cubed. So this one will be a factor of y. Finally, 2b. 2 is fine and the b is fine. They are both less than or equal to the amount of prime numbers that we have in our prime factorization. So it turns out that only 2 of these are not factors of y. This one because it is actually larger than the value of y. And this one over here because it has too many of the prime factor b. Before we do more questions, I just want to go over a few definitions. Now, we've been using factors up to this point in doing our prime factorizations, so I'm sure you understand what they are, but I just want to confirm that factors are numbers that multiply together to make another number, and that a factor will always divide the number it came from exactly. They will always be smaller than the number they came from. Multiples, however, will always be larger, and that's because they are numbers that appear in the times table. A multiple will always be able to be divided by the number it is a multiple of a certain number of times without leaving a remainder. It is also important to remember that every number is both a factor and a multiple of itself. For example, 6 is a factor of 6 because 6 times 1 equals 6. 6 is also a multiple of 6 because it appears in its times table. The highest common factor is the largest factor that is common to both numbers. So if you thought through all of the factors of both numbers, noted the ones that were the same, and then picked the highest one, you would have the highest common factor. Lowest common multiple is when you look through the times tables of both numbers and you find the first number that is the same and in both of the times tables. It helps to remember that although highest common factor, or HCF, begins with the word highest, the result of doing that is always a number that is smaller than both of your numbers, or equal to one of them. And with lowest common multiple, again, even though it says lowest, it is actually a number that is larger or equal to your numbers. Now we're going to go through some questions where we have to find the HCF and the LCM. In this question, we need to find the lowest common multiple of some pairs of numbers. Now I'm going to show you a couple of different ways to deal with finding the LCM and then the HCF in the next question. First of all, I'm going to show you a way using something called a Venn diagram. Now for both the methods that I'm going to show you, we are going to need to do the prime factorization of each number. So let's start by doing 28. Remember, we use the factor tree to lay out our working. 28 can be divided by 2 to give 14. It can be divided by 2 again to give 7. And then we have that 28 is 2 squared times 7. 42, let's see how that goes. That can be split down to 21, which then can be split into 3 and 7. So 42 would be 2 times 3 times 7. So a Venn diagram is going to look like two circles with an overlap. We label with one of the circles with one of the numbers, so 28, and the other one as 42. Now in the middle, in the overlap, you need to write any prime numbers that appear in both of the factorizations. Now, so when you draw them, you need to make sure that your overlap is large enough to fit some numbers into it. Now 2 appears once in 42 and twice in 28. So we can put 1, 2 in the middle. 3 only appears in 42. It does not appear in 28, therefore we cannot put it in the overlap. 7 appears in both, so 7 goes in the overlap. Now we go through for each of the circles and fill in any extra prime numbers that we need for our prime factorization. For 28, we need an extra 2. So that the whole circle of 28 has 2 2s and 1 7. 42 needs to have a 2, a 3 and a 7. At the moment it only has a 2 and a 7, so we need to add a 3. Now that we've done our Venn diagram, to work out the lowest common multiple, we just need to multiply every number that appears in our Venn diagram together. So the LCM will be 2 times 2 times 7 times 3, which we can write as 2 squared times 3 times 7. Most of the time it's okay to give your answer as a product of prime factors in index form, and sometimes you may be required to actually write the answer out. This is 2 times 3 times 7, which is 2 times 42, which makes it a little bit easier to work out as 84. So what this has done, by putting it into a Venn diagram, we have been able to make sure that we find the lowest common multiple, because one of the multiples of 28 and 42 that is common would be 28 times 42. But there are numbers that are smaller than that are still in both the times tables. And by putting it into a Venn diagram, we've made sure that we have not counted prime numbers that appear more than once across the two prime factorizations. So if we just multiply these numbers together, then we'd end up with 2 times 2 times 2 times 3 times 7 times 7. But we haven't counted one of those 2's and one of those 7's twice because we put them in our overlap. So it works quite nicely. In part B, I'm going to use a slightly different method if you're not a fan of the Venn diagrams. We still need to use our prime factorizations though, so let's start by doing that. 54 halves into 2 and 27. 27 can then be divided by 3 several times. So 54 is 2 times 3 cubed. 90 can be halved, and then it can be divided by, well, we check, 4 plus 5 is 9. 9 can be divided by 3. So 3's into 45, 3's into 4 goes 1, carry 1, 3's into 15 goes 5. Oh, I've done that the wrong way around. So we need to put a 3 here, and then we put our 15 on this side. We can get another 3 and a 5. So 90 will be 2 times 3 squared times 5. So the way we can do LCM without using the Venn diagram is to go through every prime number that appears in our prime factorizations and take the highest power that we see. So it's kind of the opposite, as a way to remember it. Lowest common multiple, you pick the highest power of each prime number. So we start with 2. We look at the 2's. These are both 2 to the 1, so we just take a 2 to the 1. Then we look at the 3's. There's 3 squared and there's 3 cubed. We take 3 cubed because we take the highest power. Then there's 5's. This one's 5 to the 1, and there is no 5 in 54's prime factorization. That's because it's 5 to the 0. 5 to the 1 is the higher power, so we take a 5. So our LCM is 2 times 3 cubed times 5. 3 cubed is 27, and 2 times 5 is 10. So the answer is 270. I will do part C using a Venn diagram and part D using the method I just used, so that you've got a couple examples of each. Let's break 60 down. So we get 2 2's, a 3 and a 5. So 60 is 2 squared times 3 times 5. And then we've got 48. So 24 splits down again. 12 splits again to 6. Splits again with a 3. So this one would be 2 to the 4 this time, times 3. So we need to make sure they don't have to be perfect circles, as you can see from my example. But we need a big enough overlap. Okay, so that's what I was concerned about there, making sure that we had a big enough overlap. Things that are the same. So there's definitely some 2's. Now there are 2 2's in the 61 and there are 4 2's in the 48. So 2 of those can go in the middle. We also have a 3 that is common in both, but that's all because there's no 5 in the 48 one. For the 60 circle, we need 2 2's, a 3 and a 5. We've got 2 2's and a 3, so we need to add a 5. In the 48 circle, we're missing 2 2's, so we need to put those in, which means that our LCM is 2 times 2 times 2 times 2, so I'm counting up all my 2's first, so 2 to the 4, multiplied by 3 and multiplied by 5. Quick way to work this out, well, 2 to the 4 times 3, that is 48. And then we just need to multiply it by 5. Quick way of multiplying by 5 is to multiply by 10, so that's 480, and then halve, which is 240. There we go. Okay, last one. So 240, right, I'm going to cheat a bit here, because in the last question, I worked out that the LCM was 240, which means I've already got the prime factorization, so to save time and space, 240 is 2 to the 4 times 3 times 5. And I will have to do 756 though, which is quite a large number. So 2, so let's think about this. 700 halved is 350. 50 halved is 25, so that's 375 so far. And then 6 halved is 3, so we had 375. That's now 378 because we add the 3. We halve again. Half of 300 is 150. Half of 70 is 35, so that's 185. Half of 8 is 4, so 185 plus 4 is 189. That can no longer be halved, but does it divide by 3? Well, 1 plus 8 is 9, plus 9 is 18, so yes, it does divide by 3. So we can pop a 3 branch down. So 3's into 18 goes 6, 3's into 9 goes 3, 3 goes into this again, 21, and we have another 3 and a 7. So 756, we have 2 2's, so 2 squared, 3 3's, 3 cubed, and a 7. So remember, LCM, lowest common multiple, is the highest power of each prime number. For the 2's, the highest power is 4. For the 3's, the highest power is 3. And for the 5's, the highest power is just to have a 5, 5 to the 1, and the same for the 7. I'm going to leave that as a product of prime factors, because for a question like this, I believe that they would not expect you to multiply this out in your head. Now we are going to find the highest common factor of some pairs of numbers. And the process is very similar to the one for LCM. We will do both methods like we did in the previous question. Now, to make this a bit quicker, I am going to write down the prime factorization of 48 without drawing a prime factorization tree. The way to do this is to start again with our smallest prime number that goes into it. So we know that 2 goes into 48, so we can write down a 2. Then we just keep dividing and noting what we are dividing by as we go. So when we divide 48 by 2, we get 24. 24 can also be divided by 2 again to give 12. 12 can be divided by 2 to give 6, and 6 can be divided by 2 to give 3. So 48 splits down into 2 to the power of 4 times 3. 64 can be divided by 2 to give 32, by 2 to give 16, by 2 to give 8, by 2 to give 4, and by 2 to give 2. So 64 can be written as 2 to the power of 6. Now you can miss out prime factors in doing that method, and you can lose your way. So I only suggest that you do this if you are very confident with your division and keeping track of things in your head. I have done it just now, just to be a little bit quicker, and you have plenty of examples of factor trees in this video earlier on. Now we're going to use the Venn diagram method like we did in part A of question 4. I'm going to draw myself 2 circles. I'm going to make them reasonably large to make sure my overlap is good. So I've got a 48 and a 64, so we fill it out in exactly the same way we did for LCM. Things that are common, well, there's 4 2's, so 1, 2, 3, 4. 48 has an extra 3, and 64 has 2 extra 2's. Now where LCM was multiply everything in the Venn diagram, HCF is just multiply everything in the overlap. So highest common factor here then would be 2 to the power of 4, because there are 4 of them, which is 16. Okay, so 24 can be halved to make 12, and halved to make 6, then halved to make 3. So 24 is 2 cubed times 3. 56. This number can be halved to make 28, which can be halved to make 14, which can be halved to make 7. So 56 is 2 cubed times 7. Now we're going to use the different method where we go through and we look at each prime number and its power. So for LCM, we looked for the highest power of each prime number that appeared. For HCF, highest common factor, we look for the lowest power in each prime number that appears. For 2, we have a power of 3 in both of our prime factorizations, so the lowest is just to take 2 to the 3. For the 3's, we either have 3 to the 1 or we have no 3's, which is like having 3 to the 0. So the lowest power here is to not have a 3. And it's the same for the 7. There is no 7 in the prime factorization of 24, so we do not take a 7 in our HCF. Therefore our answer is just 8. 63. This cannot be divided by 2, so I'm going to start by dividing by 3. I can divide 63 by 3 to get 21, which can be divided by 3 again to get 7. So we have 3 squared times 7. 315. This cannot be divided by 2 either, so I will start with 3. 3 goes into 315 to give 105. Sorry, 105, so 105. Can 105 be divided by 3? Well, 1 plus 0 plus 5 is 6, so yes. So I can divide by 3 again. 3 is into 105, well 3 goes into 10 3 times, take 1 over. 3 goes into 15 5 times, so that gives us 35. 35 cannot be divided by 3 because 5 plus 3 is 8. 35 can, however, be divided by 5, so now I can note down a 5, and 35 divided by 5 is 7. So 315 is 3 squared times 5 times 7. Now we're going to do the Venn diagram method again. So I draw my circles, decent sized overlap, 63, 315, things that are the same. 2 3's are the same, and a 7. 63 doesn't need any extra numbers, so I don't need to put anything here, and 315 needs an extra 5. So my HCF is the product of the numbers in the overlap, which is 3 squared times 7, which is 9 times 7, which is 63. So the highest common factor is 63, which is predominantly because 63 it does actually go in to 315 when you multiply it by 5. Don't be put off if this happens, it's perfectly valid. Right, 240 and 756. Now we did do these two numbers in the previous question, so I'm just going to write them down from there. 2 to the 4 times 3 times 5, and our 756 came out as 2 to the 4, 3 cubed, and a 5 and a 7. So back to the other method where we go through each prime number and take the lowest. 2 to the 4 and 2 to the 4, we take those. 3 to the 1 or 3 cubed, take the lowest power, so I take 3. The 5, same power in both, so I just take 5, and the 7, that only appears in one of them, so I take the lower power, which is not to have one. So we are done with our HCF. Let's see what we've actually got here. 2 to the 4 is 16 times 3 is 48, so that's 48 times 5. Remember what I said before, times it by 5 to a large number, you just times by 10, 480, and you halve 240. So key thing to remember, if you're using a Venn diagram, then everything in the Venn diagram multiplies to make LCM, just the overlap multiplies to make HCF. If you're not using a Venn diagram, then lowest common multiple takes the highest power of each prime number, and the highest common factor takes the lowest power of each prime number. This question is more of a problem-solving question, where we're going to have to work backwards. We have been told that two numbers, both below 100, have got a particular HCF and an LCM. Because we've been working with prime factorizations to work out our HCF and LCM, we should use the prime factorizations to help us with this question. So our HCF is 12. Let's write that down as a product of prime factors. I can halve 12 to give 6, and I can halve again to give 3. So 12 can be written as 2 squared times 3. Our LCM is 420. I'm going to do a factor tree for this one because it's a bit bigger. If I halve this, I get 210. If I halve again, I get 105. This cannot be halved, but it can be divided by 3. 3's into 10 goes 3, remainder 1, so it's 35. 35 cannot be divided by 3, but it can be divided by 5 to give 7. So my LCM comes out as 2 squared times 3 times 5 times 7. So if we think about the Venn diagram for this, we can't label our circles because we don't know what the two numbers are. But we do know that there's a 2, a 2, and a 3 in the overlap. And there's nothing more in this overlap because if there was, our HCF would be larger. If we look at our LCM, we now know that 2 squared is already in the overlap, so we don't need to worry about that. And our 3 is already in the overlap, which leaves us with a 5 and a 7. Now, there are several options of where these numbers could go in our Venn diagram. We could have them both on one side, so a 5 and a 7 in one half of the circle, and nothing in the other. Or we can have a 5 in one and a 7 in the other. Now, there is actually something in the question that tells us which one of these two options it is. It tells us that both numbers are below 100. And if I put both 5 and 7 in one of these circles, then that circle would multiply up to more than 100. So it must be that there's a 5 in one circle and a 7 in the other. Now we can work out what the two numbers are. This number on the left circle is 2 squared times 3 times 5. To work this out quickly, I would take a 2 times 5 to be 10 and the other 2 times 3 to be 6. So one of these numbers is 60. The other circle is 2 squared times 3 times 7. This could be written as 4 times 3, which is 12, then times by 7. 12 times 7 is 84. So my two numbers are 60 and 84. They are both below 100 and they have the correct HCF and LCM. This question is a question in context. That means that it does not say in the question that you need to find either the LCM or the HCF. Instead, it gives you a particular scenario where it turns out to be helpful to use those concepts. These, I would say, are the hardest type of questions that you will come across because it may not always be clear to you what you need to do. If we have a think about this question in particular, then we are told that both bells ring at 12 p.m. We then are told that A rings every 4 minutes and B rings every 9 minutes. How many times will the bells ring at the same time in the 3 hours from 12 p.m. to 3 p.m? We need to work out how long it takes for the bells to ring again at the same time. And if you really think about it, all that's asking us to do is work out the LCM of 4 and 9. One of the ways you might approach this is to start writing out the times table for each number until you come across a number that is the same. This can take a small amount of time, and if these numbers were larger, it would definitely take probably too long, really, for the time you should be spending on this question. So, we are going to use the methods that we've been using up to this point. LCM of 4 and 9. So, we need to split them into their prime factors, which is actually very easy because 4 is just 2 squared and 9 is just 3 squared. In terms of the Venn diagram, there isn't going to be anything in our overlap. That tells us that the lowest common multiple of these two numbers is actually just the two numbers multiplied together, because when we multiply everything in the Venn diagram, we just get 4 times 9. So our LCM of 4 and 9 is just 36. That means that they will ring at the same time every 36 minutes. Now we just need to work out how many times this happens in 3 hours. Don't forget that 1 hour is 60 minutes, which means that 3 hours will be 180 minutes. So this question is basically asking us to do 180 divided by 36, because that will tell us how many lots of 36 go into 180. This would be on a non-calculator paper, so we have to do this in our head. The easiest way to deal with a division like this is to simplify the fraction. I can halve both the top and the bottom. 180 halves to 90, and 36 halves to 18. I can keep doing this until the calculation is much nicer. 45 divided by 9 should be something that's fairly easy to do, because we know our times tables very well. 45 divided by 9 is 5. So our conclusion is that they will ring at the same time 5 times in the 3 hours from 12 till 3. So look out for these questions. They generally tell you about something that happens every certain amount of time, which means that you're effectively looking for the lowest common multiple. And this brings us to the end of the video. Now we're just going to go over a few things that you need to remember when you're dealing with questions in this topic area. First of all, 1 is not a prime number. Don't forget your definition that a prime number has exactly 2 factors. Also, sometimes people make the mistake of thinking that 9 is a prime number. I think that's because 9 is the first odd number that is not prime. Make sure that you don't get factor and multiple the wrong way round. Factors are always smaller and multiples are always larger. Remember, for highest common factor, if you draw a Venn diagram of the prime factors, it is just the product of the overlap. And with lowest common multiple, you just multiply all the numbers that appear in your Venn diagram together. Please make sure that you know your times tables. It is very easy to make a mistake doing prime factorizations if you are not confident with your dividing and multiplying. Thank you very much for watching, and I hope you found it helpful. Please support the channel by clicking on the like button and subscribe if you'd like to see more. I look forward to seeing you in the next one. Bye!